Hi everyone, welcome back to Sigma Maths. This is the last video in the Exponentials and Logs series, and we will be looking at modelling. You will be expected to apply what you have learnt so far with exponentials and logs to a range of real-life situations such as radioactive decay and population growth. Before we start looking at some questions, I just wanted to give you an idea of the types of models that we will be looking at. On the top left here, we've got one of the most common ones you'll see, which is exponential growth. This is most commonly applied to something like population growth, and if you have a look at this generalized equation here, P would be the population after T years, for example, and P0 would represent the initial population. So in this sketch that I've got here, you can see it passes through 20. That would be an example of P0. This model is good for anything that is expected to grow exponentially. It also has a special property that we have seen in previous videos, where if you differentiate P, which in this context gives you the rate of population growth, you get a constant multiplier of the original function. So here you get k times P0 e to the kt. So effectively some constant times the original population. We also have exponential decay, which is where we have the same exponential model but with a negative power of e, which has the effect of flipping the exponential graph in the vertical axis. So what we have instead is a depreciation. So this could be used for the depreciation of something like a car, and you can see that it tends to zero over time. We also have growth to a limit. So this is where we take the exponential function and we're going to flip it in the vertical axis and the horizontal axis, as you can see by this equation, which allows us to have growth but with an upper limit, so some kind of cap, maybe carrying capacity of the environment or a certain amount of food that's available for a particular species. And then finally we may also encounter logarithmic growth, which is where we need something to grow very slowly but not to have a cap on it like it did with the growth to a limit example above. Okay, so this line has a similar shape to the one above, but this line will continue to grow, but at a diminishing rate. Okay, let's have a go at some questions so we can see all this in practice. Question 1. Okay, this question is all about radioactive decay. We have been given an equation in the question. Explain briefly why k must be negative. There's your k up here. So this is because we are dealing with decay rather than growth. If it was growth, we would have a positive k, but because we are dealing with decay, we need it to be negative. So the model represents decay, not growth. This is why we need a negative power of e. Okay, part B. Given that after 120 years the mass of the substance is 130 grams. So here we have T is 120 and M is 130. So this is all, dealing with these questions is all about picking out the information that you actually need and trying to see through most of the words or understand what they mean. So if we put these numbers into our equation, we would have 130 equals 200 e to the 120k. The k is the thing we're trying to find, so this is a case of just solving an exponential equation. So we would divide by the 200 e to the 120k, and then if we take logs, natural logs of both sides, we'd have 120k equals ln of what will be 13 over 20 if we simplify. There we go. And then to finish off, we just need to divide by 120. So ln of 13 over 20 divided by 120. Let's see what we get. Okay, so we get negative 0.00. Let's just check what it says in the question, giving you answer to two significant figures. So negative 0.0036. Okay, so now we have our full model. Just going to make a note of that up here. So it's 200 e to the negative 0.0036 t. So negative k as we expected. Okay, part C, let's do that up here. Find the time it takes in whole years for the mass of the substance to be halved. Okay, so we need to take the initial mass. So this requires us looking at the model and understanding what the initial mass is going to be. So initial mass. Whenever you see the word initial, we're talking about t equals 0. So the initial mass here will be when t is 0. So if you put t is 0 into here, we get e to the 0. E to the 0 is 1. So the initial mass is 200 grams. Okay, so if we're looking to how long it takes for the mass of the substance to be halved, then we are looking for when it is 100 grams. So we're going to put in 100 for m equals 200 e to the minus 0.0036 t. We are again solving for t. So let's see if we can do this all in one go. So we are going to do 100 divided by 200, which is 1/2. We are then going to need to learn our half to get the negative 0.0036t out of the exponential function, and then we will need to divide by the negative 0.0036, which would have been up here, multiplied by the t. Let's pop that in our calculators. Okay, and we get 192.54. So how many whole years does it take for the substance to be halved? Well, that would be 193 years, because it becomes halved somewhere between 192 and 193 years. So 193 whole years for the substance to be halved. Okay, part D. Sketch a graph of this model. Okay, so I'm going to draw myself some axes. We've got m on the vertical axis, t here. Okay, so we've got an exponential graph, but we have a negative exponential, so e to the minus something t. So remember, we're not going up like this. Negative in the exponential flips it in the y-axis. So I'm going to be coming down like that. We're coming down through 200 because that's our initial value. I'm coming down. Oh dear, we struggle to draw these ones. I'm going to come up like that. There we go. 200, and then it comes down and decays exponentially, tending to an asymptote on the positive t-axis. All right, last part, E. Show that the rate of decay, now this is important word, rate. This means we're doing differentiation. Can be written as dm dt equals am, where a is a constant to be found. Okay, well, let's jump in and work out what dm dt is. So this is using our result that when you differentiate e to the kt, it differentiates. So if I do d by dt of that, we get k e to the kt. Just a little reminder up there. So dm dt, therefore, will be, we bring down the constant in front of the t here, so negative 0.0036 times 200 e to the negative 0.0036 t. Okay, so they've asked us to find a, which is in front of m. So don't be tempted to multiply these two numbers together, because actually we want to keep the 200e to the negative 0.0036t separate, so we can now replace it with m, because this here is the original function m. We are done. We can now just state that a equals negative 0.0036. So this also reinforces the idea that we are decaying, because our rate of decay is negative, which means it is decreasing. Again, also fits in with the graph because we can see the mass is going down over time. Okay, question 2. All right, this is about the growth of population of ants. We're reducing a colony of ants to a closed environment, and we again have a model given to us in the question here. P is number of ants and T is measured in days. Find, according to this model, the initial number of ants. Okay, so there's that word initial again, initial meaning T is 0. So we just pop that into our model, 422 e to the 0. E to the 0 is 1, so we know we're starting with 422 ants. Part B, the number of ants after 30 days. Okay, well, t is measured in days, so this is just popping t equals 30 into our equation. P equals 422 times e to the 30 over 50. See what we get. Okay, we get 768.9. So that's not quite 769 ants. So we would give an answer of 768 whole ants after 30 days. Part C, the rate of increase, there it is again, rate of the number of ants at the end of the 10th day. So that's t equals 10. So we're doing rate, which means we are doing dp dt. So look out for the word rate. So we're bringing down our number in front of t and multiplying it by the function. So the 1 over 50 from up here comes down. That's the k in this case. And we are evaluating this when t equals 10. So let's pop that in our calculators. Okay, and we get 10.3. Now we can leave that as a decimal, that's fine. 10.3 ants per day, if we're going to understand what it means in the context of the question. That's the rate of increase on the 10th day. The rate of increase is changing as the days pass, though bear in mind that's not the rate of increase the whole time. Part D, time taken for the number of ants to first exceed 3,000. So we're going back to the original equation, 422 e to the t over 50, and we are exceeding 3,000. Okay, so we need to divide by the 422, and then we will be taking ln of both sides, so it's going to be ln of 3,000 over 422, and then we're going to be multiplying up by the 50, because this would be t over 50. Let's see what we get for that. So we get 98.068. We need t to be larger than this, so therefore it takes 99 days for the number of ants to exceed 3,000. All right. Question 3. Okay, so a bead is projected vertically upwards in a jar of liquid. So we've got initial velocity there. Straight away we're spotting that's when t equals 0. We've got 11. Its velocity v at time t seconds after projection, so it's in seconds, is given by this equation here. Find the value of c and then sketch the graph of v against t. Okay. So the value of c. Let's put in some information that we already know. So, I mean, this is a tricky question because it doesn't explicitly say, given that when t is 0, v is 11, you need to pick up on that information from that first sentence. So we can put in 11 equals c e to the 0 minus 2. E to the 0 is just 1. So then if we add the 2 over to the other side, we get c is 13. So now we're working with v equals 13 e to the negative kt minus 2. Okay, so we're going to have to make the assumption here, it should really have been said in the question, that k is positive so that we know which way around to sketch our graph. Now, this graph is going to go into the negatives. Now, normally in modelling, we don't expect our graphs to move out of that first quadrant because usually it relates to time, so that usually stays positive, and then it's usually something like value or population or concentration or something that tends to not go negative. In this question, however, we have got velocity, and velocity can take a negative value because it is a vector quantity. So there is not a problem here that we will be going down into the negatives. So let's just think about this carefully. If we had an exponential graph, we would be going up like this, but it is a negative power, so we know we're coming down the other way. The 13 just means that we will go through 13, that we would have gone through 13 on the vertical axis when t is 0. before the -2 transformation, but because we are subtracting 2 to the whole function, we are moving everything down by 2. So we have an asymptote along here, which would have been the t-axis, but is now moved down to t as -2. And then we have the velocities coming down. I'm going to go going up because I always mess it up otherwise. So we're coming away from this asymptote up through there. Okay, so here, careful not to put this as 13. This is actually 11, which lines up with our initial velocity of 11 in the question. And then we can see that we are decelerating as we go, as the velocity goes up through this liquid. Then it obviously stops, and then it turns around, and this negative velocity just means it's coming back down again. Okay. Given that the bead has a velocity of 6.5 after 4.8 seconds, so that's t and that's v, find the value of k. Okay, so now we're finding the constant, the unknown constant in the equation using some extra information. So 6.5 equals 13 e to the minus 4.8k, so we popped our t value in there, minus 2. So a bit of rearranging, e to the minus 4.8k would be 8.5 over 13, and then k, we would get to k by doing ln of the 8.5 over 13, and then we would divide by the minus 4.8. So let's see what we get. Okay, so just check what we want it to. 4 decimal places, so we are getting 0.0885. We'll stop there because it is 2 4 decimal places. Okay, so we've got our k. Part C. Find the time taken for its velocity to decrease from 10 to 3. So we've got 2 values of v, and we want the time it takes to go from one to the other. This is quite a bit of work, so we're going to have to pop 10 in first to find out the value of time. So this is negative 0.0885t minus 2. So we need to rearrange this to find out what t is. Okay, so we're going to have what, 12 over 13. If we add the 2 and divide by the 13, we're going to be doing ln of 12 over 13. And then we will divide by the negative 0.0885. Okay, let's do that one. Okay, so that doesn't take very long at all. 0.904, just do to 3 sig fig for now, seconds to decrease from 10. So if it started at 11, it's not surprising that it barely even takes a second to go down to 10. Now we're going to see how long it takes to go down to 3. So putting it into the same equation, 885t, take away 2. Rearranging again a very similar way, so it's going to be ln of this time 5 over 13, because we did the 3 plus 2, over the negative 0.0885. Okay, and we get 10.797 seconds. So now we're just going to subtract the first amount. So if we called this T1 and this T2, we're doing T2 minus T1 to find the time it takes to go from 10 to 3. So 9.89 seconds. Okay, and then finally part D. Okay, so this actually is quite a bit of mechanics in it, this question. The acceleration of the bead. So this requires you to know, or at least think about the fact that acceleration is the rate of change of velocity. Okay, so acceleration is dv by dt. So this really is just to differentiate the exponential function question. So we're going to look back at our v, which I don't think we've written down anywhere in its completeness. So let's just pop it down over here. V equals 13e to the negative 0.0885t minus 2. Okay, so let's differentiate this. We're going to bring down the number in front of t. That's our k in this case. So it will be minus 0.0885 times 13e to the minus 0.0885t. And the negative 2, well, constant term, differentiates to 0. So it would be like having 2t to the 0. And then if you apply the differentiation process, 0 comes down to multiply the 2 and it immediately vanishes because 0 times anything is 0. Now we're going to evaluate this when t is 2 to find out our acceleration. And we get negative 0.964 units, meters per second to the minus 2. Okay, and this fits in with our graph. Our graph has a decreasing velocity, and acceleration here would be representing the gradient of the graph as we move along it. Okay guys, I have just realised I made a mistake in part A when I was labelling the asymptote here. This is not t equals minus 2, so well done if you spotted this and you've been saying, wait a minute, you made a mistake. This is v equals minus 2 because it is a horizontal asymptote and it would make no sense for me to put t there. Apologies for that. Okay, let's have a look at the second to last question. Question 4. So we've got a law here that is to do with the relationship between a stimulus and the sensation that you feel in response to that stimulus. We've been given a rather complicated looking equation for the model. So intensity of sensation dependent on stimulus input P with constants A and P0. Part A, show that P0 represents the threshold of stimulus input below which there is no sensation. Okay, so this is kind of wordy. You have to kind of understand what it means. So they're giving us a little bit of help here. S is 0. So we are trying to show that when P is this threshold of stimulus input, we get 0 sensation. So let's do that. If we put in P as P0 into the model, then we would have P0 over P0. So I'm just replacing that P there with P0. This would be A ln 1. And we know ln 1 is 0. So we get S equals 0 as required in the question. So actually it's quite an easy process to do, but it's just understanding what the question was actually asking for. Part B. After a particular experiment is found, the threshold of stimulus has a numerical value of 5. Okay, so that's our P0. It's 5. And we got when P is 10, S is approximately 2.08. So now we can find out the other constant A in the formula. So S is approximately 2.08, sorry. And that therefore equals A ln, now P was 10 when S is 2.08, so 10 over P0, which we were told in the question, is 5. So A therefore is 2.08 divided by ln 10 over 5, which is 2, which gives us 3.0008. Well, I'm just going to leave that as 3. There we go, found the constant value of A. Part C. Use the model to predict the value of the stimulus input if the intensity of sensation is found to be 4. So the intensity of sensation S, if that is 4, basically what's the value of P? So let's put that in. 4 equals, with our new constants that we found, ln of P over 5. Okay, so ln P over 5 will therefore equal 4/3. P over 5 equals e to the 4/3. That's undoing the ln, raising both sides to the power of e. And then if we multiply up by the 5, we have now got the value of P. So this comes out as 18.96, etc. What does it want? 1 decimal place. So that would be 19.0. There's no units to give in this question, so we are done there. The value of the stimulus input would be 19. Part D, using a sketch, explain why the model is not valid for P is less than 5. So we have no choice but to do a sketch here, because it doesn't say using the sketch or otherwise. So let's set this up. So this would be S against P. Right, so we are looking at 3 lots of ln p over 5. So we're thinking about the ln graph. Now the ln graph looks like this, and it goes through 1 normally if it was just ln x, or ln p in this case. This dividing by 5, so we're thinking back to our transformations. If we multiply inside the function by 1/5, then we do a stretch in the x direction, but we do it with the inverse scale factor to the one that we have here. So if it's multiplied by a fifth inside, it means that actually we're stretching by a scale factor of 5 on the graph, which means that rather than going through 1, we will now go through 5. We are not going to move the asymptote because 0 multiplied by 5 is still 0. And the stretch of 3 outside the function will stretch in the vertical direction, but not that we would really notice it on a sketch. So we would have an asymptote down here. So we would have the asymptote coming down from the negative vertical axis, and it would just go along like that, probably less steep than that, but I'm not going to redo it, that's fine. And we go through 5. So here we can see if p is less than 5, s is less than 0, which is not possible. As sensation cannot be negative. That makes sense. There we go. Okay, so there's a limitation to this model. It's only usable for values of p larger than 5. Okay, last question. So a bus company has bought a double-decker bus for £50,000. They would like to model the depreciation of the bus in 10 years. The company's financial advisor has suggested 2 possible models. Okay, part A. Use both models to predict the value of the bus after 1 year. Okay, so model 1 would be 50,000 times e to the minus 0.21, and model 2 would be 45,000 times e to the minus 0.23 plus 5,000. So let's pop this in our calculator and see what we get. So we get 40,529 pounds and 21 pence for model 1. And then for model 2, we get £4,754 and 1 pence. Okay, so the comparison then would be that we get a similar value for both models, but we do have that 2 slightly higher. Okay, part B, do the same thing but after 10 years. Okay, I'm just going to pop these into the calculator, I'm not going to write them out as well. So for the first model, after 10 years, we get £6,122 and 82 pence. And for the second model, we get £9,511 and 65 pence. So this time the comparison is that model 2 gives a much larger value after 10 years. Okay, part C, sketch a graph of both models on the same axis. Okay. So let's draw on axes. So we've got time and value of bus. Okay, so they are both negative exponential graphs. They're both coming down and have asymptotes, but we have the difference of model 2 has an asymptote of 5,000. So I'm going to draw in the asymptote first. So that's b equals 5,000. So we will have one model that comes down like this, and then the other model will come down in a similar way, but will go down to 0. And they both start at 50,000. You can check here, if you put t as 0, you get 50,000 here. Put t as 0 into model 2, you get 45,000 times 1, plus the 5,000 also brings it up to 50. So they both have the same starting value, but we have this difference that model 2 levels off at 5,000, whereas model 1 just goes right down to 0. Part D, interpret the meaning of the constant 5,000 in model 2 and suggest why it might be a more realistic model. So the meaning in this context would be basically the value of the bus can never decrease below 5,000. So the value of the bus cannot go below £5,000. This is more realistic because the bus will always have a scrap value, as the bus will have a scrap value. Okay, so that's the kind of reasoning that you'd have with a question like this. Okay, so that brings us to the end of our exponential and modelling video. We've seen a variety of contexts, and you've seen in almost all of the questions you are required to do a sketch. So your sketching of exponential and log functions needs to be very good to do these questions successfully. And you also need to appreciate how useful the sketches are in showing you how the model behaves over time, and therefore allowing you to evaluate how good the model is for large periods of time. So here the model 1 isn't particularly good because it suggests that the bus will have no value given enough time passing. Okay, so if you liked the video, or if you found it helpful, then please don't forget to hit the thumbs up button and subscribe if you'd like to see more. I very much look forward to seeing you in the next one. Bye!